Hey everyone, welcome to the last section, which is of this week, which is section 2.3, which are set operations. The objective of this lesson is to determine the intersections of sets. So which ones do they have the same elements? What are the unions of the sets, the combination of those two? Determine the difference of two sets. List and make the use of ordered pairs. Determine the Cartesian products of sets. Analyze sets and set operations with Venn diagrams and apply De Morgan's law for sets. So these are the things that we're going to be doing in this section. So let's get started. Let's talk about what are intersections of sets. An intersection of sets A and B is written as A and B. It looks like this. That means that what are the common elements from both A and B? So A and B is elements that live in A and in B at the same time. So let's look at an example. 1, 3, 7, and 9. What is the intersection? They match at 1, at 3, at 5. And that's it. So the intersection is at 1, 3, 5, and that's it. What about the intersection between 2, 4, 6 and the empty set? Well, the empty set doesn't have anything in there. So what do they have in common? Nothing. So 1, 3, 5, and nothing. Letter B, they don't have nothing in common. Because one is the empty set and doesn't contain any elements. So the intersection was what highlight or circle what they have in common, and that's exactly the and. Now, union is a little bit different. The union of sets of A is written as A or B, which is the set of all elements belonging in either A or B. So you can be there in A or in B. So, or both. So we have 1, 3, 5, 7, and 9. So we have a 1, a 3, a 3, a 5, a 5. But then you also have 7, 9, 4, and 6. So the union is mixing those together, putting them together. So you could be a 1, a 2, a 3, a 4, a 5, a 6, a 7, and a 9. This is A or B. Now look at the U, it's backwards. Now, what about 2, 4, 6 or the empty set? Well, that means it's all 2, 4, and 6 because the empty set doesn't show up. So again, when you are doing a union, you're not seeing what they have in common, but putting those together. So you have a bigger set. So 1, 2, 3, 4, 5. They're here, but then you add 7 and 9 because this one has it. So add those together, put them in the same set. Describing sets in words. So this is A and B or not C. And the next one would be, there can be different choices. You could say not in A or not in C and not in B. Look at this. The symbol means and, or, and, or, and. There is and, there is nor, or not. Okay. So B or, oops, B or not C. So again, they could be a different wording. The set of all elements that are in A and are also in B or not in C. And the other possibility is not the elements, the set of all elements. That's key. So the set of all elements, let's add that. the set of all elements in A and B or not C. Okay. What is the difference of sets? So we need to be careful. So sometimes we could say A minus B is going to be the A prime. Well, we can subtract sets. We can subtract A minus B. So we're going to be putting elements that begin in A, but not in the set B. So we have A minus B is that X are in A, but not in B. So we're just going to be removing the elements in A that exist in B because we're removing it minus B. It's difference of sets. So let's look at an example. Oops. I don't want to give you the answer right. So you want, let's say you have this universal set and you have A minus B. So we're only looking at A and B. So A is A comma B, C, E, and H. And they have B, which is C, E, G. So I need to remove the letters C and E. I'm only going to be left with A, B, and H. So what's remaining from A? That is subtraction between sets. Now what happens if we do B minus A or the complement of C prime? So let's look at B minus A first. So we have B to be C, E, G, and then we have A to be A, B, C, E, H. So what can I remove? I'm removing A elements. I'm removing E, and that's it. I'm left with CG. So B minus A, I'm left with C and G because I was only able to remove. Oh, I also can remove, I didn't see that. So let's go back. I'm able to remove E and C. So I'm actually only left with G. So G was the answer from B minus A. Now I have to do G or C prime. C prime is we're removing from the universal letters from C. So A will be removed, C will be removed, D will be removed, G will be removed, and E will be removed from the universe. So now I'm left with B, F, and H. So then we have G and we have union, B, F, and H. So then we combine them all. So it'd be B, F, G, and H as my solution. B, F, G, and H. Again, slowly, we had to first subtract B minus A. What does A and B have in common? The C and the G, so you're only left with G. And then you still have to find C prime, so you're removing C, the elements of C from the universe to give you your C prime. Okay. Order pairs. We have an order pair A comma B, where A is called the first component and B is called the second component. In general, A and B does not equal B and A. So you can't just flip-flop them. Two order pairs are equal provided that the first components are equal and their second components are equal. Of course, if you have 1, 1, 1, 1, or 2, 1 is equal to 2, 1, this is equality. But normally they will have their own independent A and independent B. Okay, this is called an order pair. Why do we need an order pair? Because we are going to do something called a Cartesian product of sets. A Cartesian product is actually uniting two different sets. So you have A comma B, where A lives in A and B lives in B. They live in two different elements. And they combine them as a point. Okay, so we're going to be finding the Cartesian product of this set. So you have A that has the set AB, and we have the set B to have 1, 2, 3. So you're going to do a combination. A will go to 1, A will go to 2. So we want A cross B. So A comma 1, A comma 2, A comma 3. So A1, A2, A3, B1, B2, B3, B1, B2, B3. And this is called a Cartesian product. What about B and B? We have 1, 2, 3 cross 1, 2, 3. So you should end up with 1, 1, 1, 1, 1, 2. Like if we were distributing 1, 3. Now you go 2, 1, 2, 2, 2, 3. Then you go 3, 1, 3, 2, and 3, 3. So you have Cartesian product 1, 1, 2, 2, 3, 3, and so on. There's your solutions, making sure that you're organizing. A will go to 1, go to 2, go to 3. B will go to 1, go to 2, go to 3. They are grouped together. Okay. Cardinal number of a Cartesian product. You may also, if the cardinality of n of A is A and the cardinality of n of B is B, you know that the Cartesian between these sets A and B is going to be the same as B cross A. So then you can multiply the cardinality of A times the cardinality of B, which is the same as the cardinality of B times the cardinality of A. All you have to do is multiply A times B. Multiply each of their cardinalities. So we're going to use this formula. We're going to multiply A times B, which are the cardinalities of the sets, meaning how many elements they have in each set. Okay. So let's find some products. So we know that n of A is 12 and n of B is 7. So then this is A and this is B. We can multiply A times B, which is 12 times 7, gives me 84. So that means that there are 84 Cartesian products. Okay, so there we have it. N of A times N of B. There it is, which is the same as N of B times N of A. So we had 7 and 12, or 12 and 7, which was 84. And that's exactly what we had. That happens when you are doing Cartesian products and you know the cardinality of each one. The last view is to talk about Venn diagrams and set operations. So this means the intersection between A and B. There's the intersection. This is the or, that means all of it, the conjunction, all of those together. A or B. So this is and, this is or. This is the complement. See how you have on the outside the A, the U, that means A prime. This is the complement. And then this one's the difference. Look at the subtraction. So you have A minus B. So it's all of the elements in A that are not in B. So all elements that are or that live in A but not B. So you're removing everything that is contained in B because all you want is A and subtracted B. So you don't want B. So example 9 and the rest of them is going to be shading Venn diagrams to represent sets. So you want to draw a Venn diagram that represents A, complement, and B. So you have a Venn diagram. So remember, I'm going to create myself a Venn diagram where I'm going to have A and I'm going to have B. And the first part is I want A prime or A complement. So the complement is everything on the outside of A, so including B, but not in A. And I also want B. So B is here. So where do those both color match? Let me change this. Where do they match? What colors? Well, they only match here. So the solution is where they shade together. So it's only this piece. This represents A prime and B because you're removing the options and there's a universe. Okay, very similar. We want to shade the complement of A or B complement and C. So again, we're going to create ourselves a big Venn diagram because I have A, B, and C. They're saying that A prime, so everything outside of A. So I'm going to make the colors everything in not in A. And then I'm going to color in B prime, which is everything in terms of B. So this is A, B. So now everything outside of B okay, everything. And then and C. So and C would mean this. So where all the three colors meet. So all of the colors meet in this area. In that C area, because you're removing the complement of A, you're removing the complement of B, and all you need is C. So you color code C. Okay, that's how you can write a Venn diagram along a solution. The last slide is to talk about De Morgan's law. So notice how there is this apostrophe, it distributes to every single thing. So now you have A prime, look at the symbol. Instead of or, it becomes and, instead of, so this is an and symbol. It's going to convert to an or, and then this is going to become B prime. Similarly, if you have an A prime, a prime on the outside, it also distributes. So it's going to be A prime now and B prime. So pretty much De Morgan's law is a distribution of your apostrophe that this comma distribution. And that will switch everything. So instead of A, it's now A prime or the complement. The symbol will also change. The symbol from this to this, they will swap because you are doing the complete opposite. You're using De Morgan's law. And so we'll do one more example. And that would be the end of section 2.3. You guys are doing great. Example 13, describing a Venn diagram using the region. Well, let's look at this. What do I see of all of them? This is not A, not B, not C, but it's actually the interaction between all of them. This is where they all intersect. So this would be A and B and C, where they all intersect. The region and color can be described as belonging to all of the sets A, B, and C. Therefore, the region represented as A or B or C. You can also separate them as A and B and then C. But in this case, because they only have one intersection, I can just do it together, all together, A and B and C. Okay. And that is the end of section 2.3. Thank you so much, and I'll see you next time. Have a good one. Bye.